Buoyancy. It's simple, right? Light things float and heavy things sink. Well, it's actually not as simple as it may at first appear, because buoyancy is more to do with how much water is being displaced by an object and whether that object weighs less or more than the water that it displaces. Take this syringe as an example. As you can see, its end is bunged up to make an airtight chamber in the bottom, and currently it weighs less than the water that it displaces, and so it floats. However, if I compress the syringe and lock it in place with its dowel, it now takes up less room because the air chamber has been compressed, and so the syringe as a whole is therefore more dense. Dense enough to now weigh slightly more than the water it displaces, and so now it sinks. It's a pretty cool concept, but you might be wondering why I'm exploring it. Well, in this video, we're going to be building a submarine. This video is sponsored by KiwiCo. More about them later. A full-sized submarine is designed to be more or less neutrally buoyant, which means that its overall sealed weight is pretty much equal to the total amount of water it displaces. In order to descend, air is compressed inside what's known as a ballast tank, making room for some of the surrounding water to enter. This of course makes the submarine slightly heavier, and so it descends. When it needs to rise again, the air is decompressed and the water pushed out, allowing the submarine to regain its original buoyancy. To copy this technique for my submarine, I'm going to use some of these massive syringes to pull water into it for the same effect. The challenge, however, lies not only in operating them mechanically, but also making a framework to support them and the control circuitry. To start this framework off, I've decided to begin with some acrylic discs. I've gone with acrylic mostly because it's easy to drill through for the various required holes, but an added benefit is that it will be transparent when finished, allowing the internal submarine workings to be seen during operation, which should look pretty cool. To link them together, I'll be using hexagonal pillar supports of various lengths, which allows me to build it up in layered sections. This first section is for the power core, which is a more exciting way of saying batteries. The ones I'm using are just 18650 rechargeable lithium cells, which can be dropped in place and held there tightly with cable ties and glue. I'm wiring them up in such a way that results in them being a 12-volt 5000 mAh battery pack, though being lithium cells they do of course need a protection circuit to prevent them from being over-discharged. This makes for a very safe high-power battery system which should provide plenty of juice for the submarine. Instead of using a normal power switch to turn it on and off, however, my plan is to use magnetically activated reed switches to trigger a latching relay, with one reed switch wired up to enable the battery power output and the other wired up to disable it. This eliminates a water leakage point because the submarine can basically be turned on and off through its external watertight casing when that gets added, instead of having to waterproof a switch. Pretty neat. So with this power section sorted, it's time to add the mechanical system that it's designed to power, which will hopefully pull the syringes in and out automatically for buoyancy control. You see, syringes of this type are designed to be operated manually, but it's actually quite simple to add a motor to them to take over this job. The motors I'm going to be using are rather small, but they have an internal gearing system which means that they spin very slowly with a lot of power, which is important as they'll have to deal with a lot of pressure. Just like with the batteries, these too can be mounted to the acrylic discs, and I'm using a small bearing and a washer for a shaft coupler to rest upon, which provides not only a slightly flexible linkage point for the next section, but will also take any downward pressure off the motor's shaft and shift it to the motor's body, allowing not only the motor's main acrylic layer to take the strain, but also the one mounted just behind it, thanks to the use of a small red pad. As for pulling tension, that can also be removed from the motor's shaft by adding a bearing on top of the coupler and clamping it down with one last acrylic layer. All of this reinforcement is important because the motor will be pulling the syringe open and closed, and the amount of force exerted could be quite large once the submarine is airtight due to it having to compress the internal air as well. The long length of the syringe plunger, however, is definitely going to get in the way, so the first job is to replace it with a fairly simple but effective mechanical solution. This basically consists of 3D printing off a replacement head and then attaching a tube to its rear, and transferring the rubber seal from the original head to this replacement. The other end of the tube can now have another 3D printed part added to it, only this one needs a threaded insert adding to its centre. This replacement plunger is about half the length of the original, but because its centre is completely hollow thanks to the use of the tube, a threaded rod can now be used to link it directly to the motor itself, which should allow the motor to pull it in and out depending on which way it's made to turn. As you can see, I've made this system symmetrical with 2 motors and 2 syringes, and this will allow the centre of buoyancy to be fine-tuned so that the final submarine will always remain level in the water. Before I can try it out though, they do need some support as they are a bit bendy. Thankfully, I made provision for some additional threaded rods to be added through the various acrylic discs, which allows me at this stage to clamp the whole thing together to make it much stronger, including some additional end caps to keep the syringes centred. Now, as these syringes need to be able to pull water into themselves without it leaking into the rest of the submarine, I'm using some silicone tubing to route the water to them through what will later be a single water inlet point to again reduce the chances of leakage. So with that done, it's time to finally try out the motors to see if they can open and close the syringes reliably. Sure enough, with a voltage applied, the motors spin, and thanks to the threaded rods and accompanying inserts, the plunger can be moved without any extra help and apparently without struggle, although we'll have to wait until later to see how well it can handle also pressurising the internal air. So this is looking hopeful, but how on earth is it going to be controlled remotely? Well, this part of the project is actually fairly simple, as I'm just going to be using a standard RC transmitter and receiver set. As you can see, this one has plenty of knobs, switches, dials and 2 joysticks, the values of which are sent wirelessly to the receiver, with this particular one having 10 receiving channels, which means that it can operate 10 different motors or servos. As motors can be quite power hungry, however, receivers can't generally operate them directly, but instead send speed data to a motor controller, which then passes power on from the battery as requested for varying speeds and rotation directions. What the transmitter can power directly, however, are servos, which work like little remote levers, and they're actually the key to getting the syringes to open and close. You see, taking a look inside one of these servos reveals that it's essentially 3 components: a control board, a motor, and a variable resistor. This variable resistor is basically what makes a servo work at all, as when the motor rotates the spindle through a set of gears, the variable resistor turns as well. This changes its resistance value, which the control board observes to know at what point in its rotation the lever is. When a requested turn angle is provided to it, the control board turns the motor until the resistor matches what's been requested, and then it stops, resulting in absolute positioning control. Very cool stuff, but how does this help me? Well, the motors I've used for the syringe control work off the same 6 volts that the servo motors do, and their internal gears means that they use roughly the same amount of power as well. So, by removing the original servo motor and wiring up mine in their place, the control boards will open and close the syringes instead, and so that they know the exact plunger positions, I earlier added a linear variable resistor inside the syringes to replace the rotary ones on the control boards so they can still be aware of the position of the plunger and act accordingly. This works remarkably well, with precise adjustments being able to be made on the fly, with the plungers then automatically moving to the requested point and then slowing to a stop, all by themselves at any point within their movement range. This should really help me to fine-tune the balance and buoyancy when the submarine is in use, which is super cool. However, as both the transmitter and receiver work at 2.4 GHz, when the submarine does descend, it'll very quickly lose the signal, because water blocks 2.4 GHz very easily. So my plan is to instead extend the receiver aerial connections up through a shielded cable that can then float on the surface of the water on a little floater. This has an additional benefit of providing a safety tether, so if the submarine loses power deep down in the water, I can actually physically pull it back up again if required. This floater also houses a video transmitter, as the plan is to mount an AV camera to the underside of the submarine, so that we can see a live feed from it, which will be fun when it goes out of sight into the depths, as we'll be able to check out water wildlife and things like that. If it does go particularly deep, I'm also adding some lights on either side of this camera, so we can still see what's going on and do some deep water exploration. So the last thing to sort out is the submarine's propulsion method, for which I need to add 4 motor controllers. These are designed for brushed motors, so have a simple positive and negative output, which is handy as instead of going with a typical propeller and rudder system, I'm going to be using some cheap little water pumps, as they are by default entirely submersible, so can be mounted externally from the watertight chamber, again removing a water leakage point that might otherwise occur if I had a prop shaft that needed waterproofing or something like that. The idea is to use a variety of them in different positions for fine control of the submarine's motion in the water, working as low-power jet thrusters. For example, the first set of pumps will be configured to push jets of water straight out from the sides of the submarine, allowing it to move from side to side. Another set of pumps will be configured to also push water out sideways, but this time they'll work in opposing directions to make the submarine turn on the spot, with no rudder required. The same goes for forwards and backwards, only there'll be an additional much larger pump added for additional forwards thrust to hopefully get some real speed going. Before these can be mounted though, the main body of the submarine needs its external casing to make it watertight. For this I'm using a large acrylic tube with a diameter that matches that of standard soil pipe, which means that it's compatible with the variety of fittings and adapters that are available for them in most hardware shops, the most important being some rubber end caps to act as seals. To allow water in for the syringes, I've punched a hole in one for a pass-through port in order to provide an inlet for the silicone tube that was added earlier, as this clamps down so tightly that the water can't leak around it and so can only enter into the submarine body through the silicone tube to supply the syringes, in a nice and controlled way. As for the other end, this can also have a pass-through port, only this side is purely for the pump and transmitter wires to exit through, so needs to be completely waterproofed with some CT1 glue. Both of these caps can then be followed up with some joiners, which not only bite the caps to help to hold them in place, but provide an extra linkage point for some more piping. The idea with these extra sections is to have the various pumps mounted inside them with their exit tubes pointed in the required directions. The insides of these will be flooded with water to supply the pumps, so to filter out any grit that could maybe jam in them, I'm using a bit of fabric draped over the inlet side that can be clamped in place with a final end cap. As you can see, this end cap has an extra camera mounted to it for another angle for us to view from, and the rear end cap has a larger tube for the much bigger forward thrust pump, as well as some fins. And with that, it should, in theory, be ready to dive. So with it all together, it certainly looks very impressive. It's a lot longer than I thought that it would be, but seeing as it's been made up as I've been going along, it's not too surprising. Now in terms of its buoyancy, I'm actually fairly confident that it's just going to be about right. I've not done any calculations, which is perhaps a bit foolish, but it's pretty heavy, so the amount of water that this central section is displacing should result, hopefully, in the balance just being about right, so that when the syringes pull the water in, it'll then go down under the surface. But I'm just going to have to test it out, and the plan is to take it to the lakes and then test it out in a proper body of water and hopefully do some challenges. However, before I get on with that, it's time for a quick ad from this video's sponsor, KiwiCo. KiwiCo make fantastic hands-on projects for kids of all ages, focused around the topics of science, technology, engineering, art and math, with a goal to educate in a fun and engaging way. Each project contains everything needed to make it, with detailed kid-friendly instructions and an educational magazine that's filled with extra content to learn even more about each crate's theme and how it actually works. For example, this Kiwi crate for 5 years and up lets you build your very own pinball setup that can be customised as you like, observing how bounce and elasticity affect the ball so you can work out how to make the best runs. For more advanced makers, this Eureka crate for 14 years and up allows you to make a proper electronic soap dispenser, which ingeniously uses a motor and bearings for the pump action, with the magazine going in depth about how this works, as well as the history of soap. With Christmas just around the corner, constructing projects like this is a great way of spending time together, working as a team to create something cool and making memories in the process. They offer 9 subscription lines catered for different age groups, with shipping available to over 40 countries. On top of that, they've got a great offer on at the moment where you can try your first month of selected crates completely free. And you can take advantage of that by going to kiwico.com/DIY perks to sign up. So again, to get your first month completely free, head to kiwico.com/DIY perks. So now it's time to take this thing to the lakes and see if it works. Let's go. So we are doing something completely different, and we're here in Coniston, and I'm here with James Wormsley from Project Air. And James has also made a submarine that mine is going to be competing against. None of us know exactly what each other have done with our submarines. So, are you ready?
Yeah, I suppose I am. Yeah, let's see what you've done.
Is it? Oh my goodness!
So,
It's like a. I can see what you mean. It does look a bit like a bomb.
yeah, yeah. We're a bit concerned taking it out in public.
It's like a U-boat or something.
Yep.
It's
so what we've
huge.
got, I'll explain it to you.
Yeah.
So that's the plan.
Yeah, brilliant. I should have expected a typical piece of DIY perks engineering with all these lovely threaded rods and.
It got out of
perspex and
hand
stuff.
very fast.
Yeah.
Originally it was going to
love
be
it.
about that big.
Right.
So, yeah, so can we see yours?
Of course. This is what I've been working on for the last couple of weeks, or couple of months actually. Ta-da!
Wow!
It's a box full of wires.
Okay, that is a completely different.
It's a different approach completely.
RC expert. It's a bottle. He's used a bottle.
He's noticed.
I like it's yellow as well. Yellow submarine.
Of course, I was a bit right. One criticism about Matt's: it's not yellow.
Oh yeah, yeah. Mine's transparent.
I love yours. No. Right. So to ballast the thing, you can take the top off on the bottle, fill it with water, the right amount of water so it's neutrally buoyant, and then yeah, basically you can use the servos on the back here, which have been waterproofed with olive oil.
Okay. But what about the motors? Like, are they okay underwater?
So yeah, I've tested them under the water. The brushless motors like this, they're completely waterproof. It's the electronic speed controllers that are the problem. So they're in this. And I've waterproofed them just in case that gets wet.
This carries all of the power then
all
as
of the power, all of the signals. I'm just going to be really cool piloting this thing first person view with a pair of goggles under the water.
Yeah. Are you using goggles?
Yeah.
I'm just using my phone.
Your phone? Yeah. That's cool. That's your USP, isn't it?
And you're colour coordinated.
Oh yeah. Team yellow.
Yeah. So before we test them out in the lake itself, we thought we'd give them a test run in a little inlet, starting with James's.
We are go for launch. Right, so first test is will it sink? So I need to put water in it. So now I've got it on the top of the water, and now I'm going to see if I can dive.
Oh yeah.
Hey, there we go. Hey. It's working, kind of.
Look at it go.
So I need more wire in the water. Oh, that's a cool view. That's a cool view. Oh, look at this. This is brilliant.
I'd love to have a look through there.
Is it stuck?
You're going into the floor.
It seems like I'm being held back.
I think it might be the wire. It's probably better in deeper water. Try and get it out as far as you can. Throw as much cable in as you can.
If it was untethered, it'd be great.
Yeah. Sadly, even in deeper water, James's submarine was still struggling with the big tether.
It's just being influenced by this tether too much. It's just so heavy. I've got very little control over it in terms of where I actually want it to go. Quick assessment, seems that we've got limited control because of the huge tether on here, so might have to come up with another solution for that.
So, with James's submarine needing a little more work, would mine fare any better? Okay, so
how are you feeling?
I am feeling neutral, actually.
Neutral? That's not a good attitude. Come on, optimism, mate.
So here we are, nice and finished at last.
The finished thing, the finished article, looking marvellous.
So here we go, the grand first test. So what we're going to be looking out for is any water entering it, because that would obviously be really bad. And also just see whether the buoyancy is roughly correct. Oh my, oh no!
What, is it too buoyant?
I think it might be quite a bit too buoyant.
Oh dear.
So we need some weights. I have brought some, but they're in the car. Right. Well, the good news is that it looks completely dry in there. So the quick fix for now is just cable tying some clamps onto the bottom. So will this be enough? We shall find out. It's a lot heavier now, I've got to say, but that's what we want.
Come on, sink, 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 sink. Sink.
Okay, so I'm going to open the syringes now. Oh, you see the water going in there. Awesome, you can actually see it going down, there's some bubbles.
It's getting quite low actually.
Yeah.
The water line is definitely creeping upwards, I would say.
So that's currently, I think, as low as it's going to go. Right, so we're not quite under yet, but we can test out the thrusters somewhat. Off we go!
Hey, we're going.
Off we go! Hey!
Oh, that's working, definitely. That's good. That's a good amount of manoeuvrability, I would say.
Wait, that's not bad.
It's going. That cable's good.
Yes.
It's a lot better than mine. I might have to upgrade mine with that.
Okay, so the first test hasn't been entirely successful, but we have learnt quite a lot from this first test, and we'll be implementing some changes to hopefully get it fully working.
Same here.
Okay, so that didn't exactly go to plan, and it is my own fault really for not doing the calculations, but this project has been done in such a short space of time and there were so many variables in terms of the water displacement by the pumps and their own weight that I thought it would just be better just to get on and build it and see what happens rather than calculate it beforehand, and well, that's what I get as a result. So my plan now is to actually weigh this thing down properly to get it to the correct buoyancy level so that it can go at least up and down, and then we'll take it from there. So to add this weight, I'm using some small steel pellets that can be measured out into 500-gram bags and then strapped inside the submarine. It turns out that I need 4 kilograms worth of these pellets to get the submarine to be neutrally buoyant, which really shows how far off my guesswork was. When closing it up this time, however, I added some PTFE tape around the end caps, followed by some stretchy tape to clamp them in place more securely, as during my tests they were close to being pushed off due to the higher internal air pressure when the syringes are fully opened. So, will it now work? So the buoyancy looks just about right now. And I'm going to turn it on and see if I can get it to descend. We are going down. We've got descent. Okay, this is exciting. So I'm just fine-tuning these knobs. Okay, it looks like we've reached neutral buoyancy. Oh wow, there it goes. Oh, it's gone. Oh wow. Okay, that's amazing. Let's look at the camera. Ooh, ooh, ooh. I can see a glow. Yay, we've reached the bottom. Look at that. Oh, that's cool. That is awesome. Yeah, hopefully it will come up in a moment. I've just adjusted the knobs again. Oh, wow, there we go, there we go. That was awesome. That was awesome. Wow, that is cool. So we just regained positive buoyancy and up it came. Wow, that was cool. So I think that's working now. And I think it's time we took this to a bigger body of water and let it stretch its legs. Now, unfortunately, the lakes are a bit far to go in one day, so I'm just going to have to find something nearby and hopefully it'll do. Imagine. I was just about to say, can you imagine if I ended up in the water? Okay, we're in. So we've gone to a bigger body of water, which is just a canal. It's absolutely freezing, but it should give me an opportunity to test this thing out and actually see it go under. So let's see how it performs. So we're turning, as you can see, we've got some jets going there. We can see the ripples in the water as the submarine is turning around. I'm going to bring in some water so that we can send it underneath. So that's the syringes pulling in water, and we've reached neutral buoyancy, as you can see. Hey, off it goes! And reverse thrust to bring it to a stop. Oh, cool! Just see the camera feed. Look at the camera feed, that's awesome. Way! It's gone right down. Okay, I need more buoyancy. Ready? Should have stopped that. Yeah, we can see it going up now on the camera feed. Up it comes. And we've reached the surface. Very cool. And activating the proper thruster now. There we go. Look at that. It's pretty good, that.
Wow.
It can go quite fast, can't it? Look at that.
On a submarine.
Oh, look, there's an insect going past. That's an interesting piece of wildlife. So although it's not the perfect area to test in, we've been able to see it go up and down, and we can see that it actually can move around in the water surprisingly well. But I think it's time to get back to the studio, get warm, and then talk about what we've learnt. Wow, well, seeing this move around in the water as reliably and with as much control as it did was really exciting, especially when it went underneath the surface thanks to the buoyancy method, which obviously was such a big focus of this video. Seeing it go down into the water and being able to explore is really exciting, and I'm looking forward to taking this out somewhere else into a better body of water than a canal and really exploring. I would of course take it to the lakes again, but it's quite a long drive away, and I need to get this video out, so this will have to do for now. But I will be revisiting this topic in the future with perhaps a refined design that hopefully will be a lot easier for you guys to follow along with at home, and I'll make the plans available as well, so you will hopefully be able to build a submarine too. And a note to James, I still want to do the challenges that we initially set out to do, so hopefully by that new design time we'll be able to make that happen. Don't forget guys, check out James's channel. He does all sorts of RC stuff, so if you enjoyed this video you will definitely enjoy what he has to offer, and he's definitely worth a subscribe, so you can find a link to his channel down below. But other than that, I think that's it for this video. As I say, it's been a completely different and fresh topic for me, and I hope you guys have enjoyed it. And yeah, I'll be refining this design in the coming months, so you have a future video to look forward to on this topic. But other than that, I'm Matt, you've been watching DIY Perks, and I hope to see you next time. Goodbye for now.